Thank you for joining today's webinar. We will begin in approximately 3 minutes. Thank you for joining today's webinar. We will begin in 1 minute. Hello, and thank you for joining us. My name is Sinan Kanatsis. As Chief Executive Officer of KCOM, it is my pleasure to welcome you to Meggitt's second in a series of webinars on transducer uses and best practices. In this webinar, we will discuss best practices to avoid ground loops and minimize noise when installing piezoelectric and piezoresistive accelerometers and pressure sensors. Before introducing our presenters today, I would like to ask a question to the audience. Have you ever experienced transducer problems related to noise or ground loops? Please take the next 15 seconds to vote. Results will be shared with our audience in a few slides. In this presentation, Tim Harden, an applications engineer with 25 years experience in customer support for sensor and signal conditioning applications, will give us a high-level introduction to noise and sources of noise, as well as grounding. He will then provide best practices for installing piezoresistive pressure sensors and accelerometers, and several types of piezoelectric accelerometers. Jim Matthews, an applications engineering manager specializing in customer support for piezoelectric acceleration measurement devices, will then demonstrate the effects of various installation techniques and share conclusions. Both Tim and Jim will answer questions at the end, which you are welcome to submit throughout today's presentation. As our thank you for watching this presentation, you'll receive a copy of all these slides at the conclusion of the webinar. Tim, why don't you start us off?
Yes, good morning. Thank you for joining our presentation. And first I must state that this presentation is limited in scope because of the topic of noise and ground loops are many times application specific. And each application can lead us to a different tangent from today's topic. So test and measurement definition of noise. Noise is any unwanted signal that is not relevant to what is being measured. We also know that noise cannot be calibrated, and it is what we strive to eliminate before we take data. Typical noise sources. Capacitively coupled noise is stray capacitance coupled into our test data, typically from power lines, noisy motors, or adjacent circuitry. Magnetically coupled noise is the effects of varying magnetic field coupled energy into our data from typical sources of AC power lines, motors, and transformers. Current coupled noise can find its way into our data from high current devices such as shakers and drive circuits through multiple ground points as well. Another form is piezorelectric effect. It's the cause from moving any cable during the test. So low noise cable is required for all piezoelectric accelerometers and proper grounding techniques, which is our main purpose for this presentation. So ground loops. Ground loops is the most common type of noise, and that's why we're having this presentation. Electrical grounds. Earth is the most common and main ground that there is. Next is power ground. Power ground for many buildings, homes, etc. is typically a water pipe or a dedicated grounding rod which is making a solid earth contact and ground connection. Then we have instrumentation ground. Typically that's the third wire common in an AC plug. Inside the instruments there's signal grounds. These grounds can be internal DC power supplies with different potentials, each of those having a different ground reference. Ground loops. Ground loops are undesired currents. It often shows up in line frequencies of 50 Hertz or 60 Hertz and their harmonics. It typically occurs when the measurement system installation has more than one ground point. The diagrams to the right, the top one, is the proper grounding technique. You notice that the grounded accelerometer has an isolator underneath it as it's mounted to the test structure, so it does not provide a ground path back to the signal conditioner. The diagram below is the incorrect form. The accelerometer is grounded. It's also grounded to the test structure, causing a ground loop for this entire system, which is not desirable.
So, this is Seen On again with another vote. We'd like to know which transducers you use most often. Many of you probably work with multiple types, so select the type you most commonly use. Please take the next 15 seconds to answer that survey. And in our first poll, we learned that 73% of our audience today have experienced both noise and ground loop problems. Another 14% have experienced noise, and 5% have had problems with ground loops. Over the next few slides, Tim and Jim are going to offer practical installation advice to prevent these in the future. Tim will start us off with best practices for piezoresistive pressure transducers.
Piezoresistive transducers. All of the Endevco pressure transducers have an isolated connection from the signal ground to the actual case of the pressure transducer. So that's important and is needed to know to properly connect this system. Though the signal ground is isolated, there may be some special applications for high potentials that could cause a problem when the sensor is actually grounded to your media or your grounding surface, and since the shield is not connected, then there could be some difficulty with this high potential causing problems with your signal. So you must be aware of it and take precautions as necessary. If you see the diagram to the right, you notice that the green, or maybe it's blue, the blue area around the bridge itself is considered the shield of the accelerometer. It is not connected to the return of the signal going to the amplifier. That is shown in the red circle, is the actual shield of the cable. So it's not connected, and that is providing the correct grounding technique for our pressure transducers. Next is piezoresistive accelerometers. These are low impedance sensors, and the output is a voltage being less susceptible to extraneous noises. Each has a shield cable assembly and a differential bridge amplifier. Endevco offers both case-grounded and case-isolated sensors. They are designed to match the proper grounding scheme by connecting the shield at a single ground point. Again, you can see the diagram to the right. The diagram shows the ground connection for a grounded accelerometer. So that also would be the proper technique, and then the amplifier would be isolated. Next is IEPE isotron accelerometers. Most likely this is the most common accelerometer in use today. Again, Endevco offers case-grounded and case-isolated accelerometers. The cables for an IEPE or isotron is not necessary to be low noise treated, but they can be used. Depends on the application, what you choose to use what you have, or to use the lower cost non-low noise cables. IEPE sensors are either case-grounded or isolated, so the proper one should be used with the signal conditioner that can match this system, being a single point ground system. The diagram to the right does not clearly indicate where the ground is. It should be either at the sensor or at the signal conditioner. I just wanted to point that out because that's not really clear in that diagram, which is depicting the typical connection for an IEPE sensor. Another form is differential piezoelectric accelerometers. All of our differential piezoelectric accelerometers are case-grounded. This is the most common type. They must be used with low noise, shielded, twisted pair cable, and it must also be used with a differential charge amplifier or signal conditioner to provide the technique of common mode rejection. Sensors of this type are primarily used with noisy jet engines and test cells. Common mode noise rejection is very key to help eliminate amplification of unwanted noise. Common mode rejection is accomplished with the sensor's plus and minus leads connected through the twisted, shielded, low noise cable and going into the amplifier. Once it reaches the amplifier, the common mode kicks in and the signals that are unwanted and common to each line is rejected. And then we reach the single-ended piezoelectric accelerometers. Again, we have case-grounded and case-isolated accelerometers. We provide these for many applications, again, which is installation and application specific, so we provide those for the customer to choose from. Again, since this is a piezoelectric accelerometer, low noise cable must be used with these. You cannot use these sensors without it, otherwise you will introduce noise, mainly due to triple electric effect. For an ideal installation, it includes the choices of 1, grounded accelerometer, 2, an isolated accelerometer, 3, the use of an isolated mounting stud, and sometimes more importantly, you could have an amplifier such as the 2775B to the right, which has a switchable isolation for the front-end signal conditioner for the different sensor types. And this concludes my portion of this presentation. So Jim, please take it from here.
Thank you, Tim. Good day to all our attendees. I'm going to transition this presentation into some applicable testing that we perform to try to validate this information that's presented. This slide is talking about the setup, or talking to the setup. We have a single-ended piezoelectric accelerometer, 2 types, a 7201, which was case-grounded, and a 7703A, which is case-isolated. Both of these are single-ended piezoelectric accelerometers, so they have a high impedance charge output. We utilized an isolated mounting stud, low noise cables, the 2775B signal conditioner amplifier, a 2911 shaker and control systems, which is shown in the upper right there, an oscilloscope, and a small motor to try to induce noise. As our system was pretty benign and quiet in the lab, we had to utilize a motor to get more noise. Also depicted on this slide in the lower right is a cutaway view of our low noise treated cable, just to identify what makes that different from a standard coax. With low noise treated cable, you typically get about an order of magnitude less noise, and that has to do with that dispersion layer, that black carbon graphite treatment you see over the Teflon dielectric, where you have the center conductor, the Teflon dielectric, and then this black coating. What it is a conductive film that bleeds any charge buildup due to cable whip back into the shield of the cable, and that way it keeps it away from the center conductor or your signal. Now, as far as the installation variations, we have a small table here to identify the variations. We went from a case grounded accelerometer with an isolated mounting stud into the single-ended grounded amplifier, and we took that through several variations to our case grounded accelerometer with a grounded mount and a single-ended floating amplifier, which is item 5. Depicted to the right is the face of the single-ended conditioner 2775B, and also in that picture you can see where we have some options to do isolated or grounded on the input line. Now, from the test results, we have an optimum to less than optimum, and we're going to go through each one of those. This particular slide shows the optimum installation, which is a case-grounded accelerometer with an isolated mount into a single-ended grounded amplifier. No noise was detected in the initial setup. We introduced some noise with a small motor to create magnetically coupled noise, which you may see in any standard test lab or in the field. Still, we had undetected noise on the signal, and we're attributing that to the low noise cable utilized. The top sweeps you can see is the standard setup benign before introducing the motor. Below is the motor introduced, and you can see we still have a fairly decent setup. Again, this is optimum, so any buildup of noise is bled back into the ground side of the accelerometer and isolated from the mount, so it keeps the electrostatic noise from getting into the signal. On the second installation, it's very similar, except we went with a case-isolated accelerometer with a grounded mounting, single-ended grounded amplifier. Effectively very similar, but potential for capacitive coupled noise is there. The electrostatic noise can get in through the line. And explaining that a little bit, when you have a grounded accelerometer, any electrostatic buildup is bled into the low side, into the ground side of the accelerometer system. When you have an isolated mount, that cuts the path for a signal back through ground, so you don't have that electrostatic buildup into the ground system, or a difference of potential. With the isolated case, you do have a potential with electrostatic buildup in there, because inside the accelerometer, your low side is still connected. It's not isolated from ground. So there is a potential between the amplifier ground and the signal of the accelerometer. The small motor created some noise, virtually undetected in the signal. Again, this is not the ideal situation, but it's very near to ideal, so it's very acceptable. It's just not the optimum. Thirdly, we have a case-grounded accelerometer grounded and mounted to a single-ended grounded amplifier. Two grounds leave the system highly susceptible to ground loops. We have a difference of potential between the two for the accelerometer mount and the signal conditioner. Little noise is detected in the initial setup, less rejection of magnetically coupled noise compared to our previous slides. You can see that on the lower sweep, where we're starting to pick up some of that noise into our signal. We have another setup where we did the case-isolated design, an isolated mounting stud, single-ended floating amplifier, no ground. No noise detected in initial setup. We did, again, I must clarify here, when we say this initial setup, we are in our calibration lab where we have a fairly benign environment, very well situated for noise. So we're introducing noise purposely, trying to show this on these graphs. So we used a small motor again to create the magnetically coupled noise. We switched to regular cables as we still did not see much noise. So we went with an untreated low noise cable, and you can see some of the effects on that graph. So again, this is a system where we have the accelerometer, the mount, the cable, and the amplifier all contributing to an optimum setup. And if you compromise any one of these steps, you're going to introduce noise. You just need to be aware of that. This is definitely not something you want to see, and I'm sure our audience has seen these type of things before and realized, okay, we've got a problem. We need to resolve our ground loop problems. This is a case-grounded accelerometer, grounded mount with single-ended floating amplifier without low-noise treated cables. So basically, we're stripping off all the anti-noise mechanisms that you would normally use in your test setup just to show what kind of noise can get on your signal line just by not adhering to proper technique. So today we have discussed various noise sources, including capacitively and magnetically coupled noise, and how they adversely affect vibration and pressure measurements when not addressed properly. Understanding the possible sources of noise, ground schemes, and proper installation techniques will optimize the test and measurement process. It's good practice. So based on these good industry practices, tests were run with various accelerometer mounting schemes, and you saw those on the slides. To show the benefit of using low noise treated cable, a single-ended piezoelectric accelerometer grounded with an isolated mount, and additionally grounding and isolating case designs were compared to verify the best combination of grounding designs. Low noise cable and grounded and floating amplifier settings all had to be taken into account. The results validated the case-grounded accelerometer with isolated mounting stud and a single-ended grounded amplifier providing the best output, the best and optimum output relative to noise. Alternatively, the case-grounded accelerometer, grounded mounting stud, and single-ended floating amplifier provided the most noise seen on the output signal. We did talk about differential piezorelectric accelerometers, and they have a case-grounded design with a low-noise shielded twisted pair cable arrangement, and that is coupled to a differential charge amplifier. These are all key to minimizing noise in a very tough environment where they're typically used. It's designed to provide common mode noise rejection and designed for these stringent applications, which, without going too much into, is beyond the scope of the webinar. However, similar noise sources and other issues may adversely affect differential accelerometer tests. We also discussed piezoresistive pressure transducers and piezoresistive accelerometers having the benefit of a low impedance voltage output into a differential amplifier. This scheme provides a measurement chain less susceptible to noise inputs. The output cable shields still adhere to the single ground point rule to minimize noise problems during test and measurement applications. We also touched base on the IEPE isotron accelerometers, and having them to maintain the same guidelines as the single-ended piezoelectric accelerometers. However, since the charge converter circuitry is built into the accelerometer, a low impedance output voltage provides the signal less susceptible to noise interference. At this point, I will turn the presentation over to Sinan for questions and answers.
Jim, thank you so much to you and Tim for sharing your applications expertise with our audience. At this time, we'll open up the floor to questions, beginning with some that were submitted during the presentation. If you have a question that you haven't yet submitted, it's not too late. Just click on the Ask a Question tab, and from there we will qualify and answer your questions. Starting with the first question that's come in, if IEPE accelerometer most to be installed on electric generators, how is it best installed is the question, Jim or Tim?
Jim, I'll take that one.
Okay.
For this type, in paying attention to the presentation that we had here, I would choose a grounded accelerometer, which is, of course, IEPE, as this person has suggested. And then I would use an isolating mounting stud. Then that is your best shield against electromagnetic and other types of noise. So that gives you 1 point common ground, which would be the signal conditioner. So the conditioner must be grounded. It cannot be floating.
Tim, I might add also, I don't know if the question is relative to a highly noise environment with an industrial application, but it could be that that would warrant even a specific design that might have a 3-pin connection where you have an internal Faraday shield. We didn't touch about that too much because we weren't getting into the industrial applications, but that might be warranted.
Excellent point, Jim.
Another question. We typically use a case-isolated IEPE accelerometer, but we do not have very good history with the isolation quality and have to add a very thin isolation between the accelerometer and the UUT. Is this a common issue?
Do you want me to take that, Tim?
Oh, go ahead.
Yeah, this is almost identical to what we just spoke to as far as the case design. Remember, when you have an isolated shield accelerometer, there's two ways to look at that. You could mount that directly and hope that that isolation on the case is adequate, but if you do have an electrostatic field or stray capacitance, there's a path through that case to the input side on the crystal inside the accelerometer. So it does then have a path back. It does provide isolation, but if you have electrostatic or capacitively coupled noise, it's not isolated from the ground on the mount. That's why you still use an isolated stud. It's just one of those things where you have to break the path to the ground side. And it has to do with the way it's a single-ended system with a high side and low side, and where the low side gets coupled to the electrostatic noise and ground, or it feeds back on the high side. So that's why you may, may not have had best success with the original mount.
Also, Jim, I would like to add in something. Many of our accelerometers are isolated due to the coating that's on it. It's anodized, it's very thin, and if you reuse an accelerometer many times, that coating can then be your ground path. So it's good to use an isolating mounting stud for this type of application as well, especially if the sensor has aged over time and the anodized coating has worn thin. So it is a good idea.
Does the off-the-shelf accelerometer come with low-noise treated cables?
Go ahead, Jim.
Yeah, well, I can only speak to our product line. We have a standard low-noise treated cable with our single-ended charge-type devices that are specified in picocoulombs per G, if you will. Our IEP or isotron units have non-low-noise treated supplied with them, but all of our charge-type units come with a low-noise treated cable, typically our 3090C line of cable.
What kind of material can we use in order to isolate the accelerometers?
Well, this is Tim, but primarily you would want to use something that's qualified for the application, meaning an isolating mounting stud is the best method to couple all of your energy. It is designed to mate to the sensor, be it adhesive mount, be it 1032 stud, whatever the type application is. That is the best technique to use because, again, you want to couple all of the energy as well as to eliminate the noise.
Yeah, and also, Tim, if I might add, there's so many variations of non-conducting medium out there. There's tapes, there's epoxies. If what happens or what you can't stray from, I know we're talking about noise here, but also you got to look at your bandwidth here. Every time you put something in between the accelerometer and your mount, now you're going to change or you're going to damp the high frequency. So you have to couple that in. It's the old it depends thing. How high a frequency does that match? Are you mechanically going to dampen it with an isolated stud or some epoxy? If it's at lower frequencies, then it's not as much of a concern, but you might want to keep that in mind.
Our next question, we typically use UD10B10 piezoelectric accelerometers with an isolated mounting stud and Megit 2775B signal conditioners set up in ISO mode. However, sometimes for higher shock levels, we cannot use the isolation studs and must use a shock stud, simple thread stud, no isolation. In this instance, what should be the ISO GND setting on our signal conditioner?
If I might ask a question, Tim, before you jump in there, you have mentioned the ISO stud and a shock stud. So I'm not quite sure. One is non-isolated and one is isolated. I guess that's a key question, what that is. I'm not sure about that. And Tim, if I'm not mistaken, if we go with the 2775B, if you're isolated at the mount, then you want to be grounded at the amplifier, and that's the switch setting should be on the 2775B. But go ahead and jump in there and maybe comment on that.
Yes, I agree, Jim, that since, again, with proper grounding technique, if the sensor is isolated as stated using an isolated mounting stud, then the amplifier needs to be grounded. So that would be in the grounded mode and not in the isolated mode. You would not want to pass that signal through the 2775B and then on to your data acquisition system. And even though it may have ISO or grounded setting on it, you would not want to do that. You would want to ground the 2775B.
The next question, do the techniques you talked about handle noise from nearby meters and other high-frequency equipment?
Yes, Tim, initially, Tim, in your presentation portion, we talked about magnetically coupled, capacitively coupled, and current coupled. So these come from different sources. So the high-frequency switching and so forth, that's going to get, and it depends on where it's getting into. Is it getting into your cable run? Is it getting into the mount of the accelerometer? Then you look at your case design, which we talked about, and also the cabling. Maybe if you're using standard coax, you should be using low noise treated cable, even if it's an IEP type, just because of the type of situation you have. Also, you might want to look at, even if it's not low noise treated cable, if it's a twisted pair or a shielded twisted pair, even for low impedance outputs, because that cancels out that magnetically coupled noise, and the high frequency stuff depends on what it is and what the source is, how it can be addressed.
Great. Can you explain common mode noise rejection with differential accelerometers?
Certainly. Again, common mode rejection is a special accelerometer. You need the differential piezoelectric type. So that's going to be a grounded accelerometer. That ground passes through the shield of the cable. The cable is unique. It is a shielded twisted pair. The shielding itself protects the entire cable length. Inside that shield is a twisted pair. The twisted pair couples to the accelerometer. That differential piezoelectric accelerometer, the plus and minus lead coming from the accelerometer is not ground reference. So it doesn't connect to the sensor. It does not connect to the shield. It goes directly to the two wires. Those two wires then go directly to the amplifier, such as was shown in the slide that I had earlier. In the amplifier itself, when you go into the amplifier, you're going into the plus and the minus of that amplifier. When you do that, any noise, any signal, any injection that is common to both of those leads throughout the distance from the accelerometer mounting to the signal conditioner, all of that is common mode. Again, when it gets to the input of the amplifier, it's rejected by the amplifier itself. And that's what's unique about this and why they're chosen and used for noisy applications such as a jet engine or where they're tested in a jet engine test cell.
Great. If we have a piezoelectric transducer with the internal circuit isolated from case and the shield isolated from case, will an overbraid connected to the case and the data acquisition box induce noise from capacitive coupling?
I would have to hear that again. I was trying to. We have a isolated case design. Is this a single-ended type and so forth? Well, to probably answer quickly rather than go back and try to rehash that, when you have a double shielded cable, you're going to get the 180-degree phase cancellation, so that's kind of the optimum way to go. As far as the shielding goes, if it's differential type or single-ended, that's going to have to look at that as far as where the ground scheme would be. So I think if you send an email, we can follow up on that better because I'd understand the question better. And our emails are listed at the end of the presentation. I think that's the best way to do it.
You got it. Looking at our next question, why are case-grounded piezoelectric accelerometers preferred to case-isolated in installations 1 and 2? Doesn't the isolated mount achieve the exact same thing?
You want me to take that one, Tim?
Sure, please do.
Oh, okay, so I addressed that a little bit earlier in the presentation, and the contrasting here is looking at the case of the accelerometer and how the low side of the accelerometer sensor output, the crystal output, is hooked up. In the first instant, we have the low side connected to the case of the accelerometer. Okay, that's one point. On the second one, it's isolated. It's not connected to the case of the accelerometer. So in the first instance, we have any kind of electrostatic buildup inside the accelerometer through the case of the accelerometer from an outside source, right? Straight capacitance. It's automatically bled down into the low side because it's case grounded. On the other one, it's not. Because it's isolated, it's not going to the low side. It actually can feed into the high side through a whole loop. So the first instance, we have an isolated stud that breaks the path of the ground plane back to the accelerometer, even though it's case grounded. So in the first instance, we're bleeding any electrostatic buildup right to ground. In the second instance, because it's an isolated case, the electrostatic charge buildup feeds around the outside and gets back into the ground loop because there's no isolated stud between the accelerometer case and the ground plane.
As a follow-up,
again, if this is,
sorry, go ahead.
I was going to say, if there is additional inquiries for clarification, again, send an email and we can correspond that way.
You got it. Follow-up question to the previous, just for clarification. If the accelerometer is on an isolated stud, the signal conditioner should be set to ground. Vice versa, if the accelerometer is not on an isolated stud, the signal conditioner should be set to isolation. Thank you.
I'll take that, Jim. For this, it's, again, you want to have one point ground. Since there are different types of accelerometers, one being grounded, one being isolated, again, you could still use an isolator if you choose. If you use one that's grounded and you don't use the isolator, then, of course, you need to isolate the signal conditioner. Vice versa is also true. Anytime you float the accelerometer, be it through an isolator or an accelerometer that is already isolated because it's designed that way, then, of course, you need to ground the amplifier. Otherwise, you will have improper grounding techniques and you will have noise in your signal. So that is the correct way to do it.
Looks like one of our final questions. Can I read a single-end accelerometer in two different analyzers? What is the proper wiring practice for that without influence on the MB reading?
I'm not sure I understand that question.
I think I do, but I don't know of a technique to accomplish it, Jim. I think they're trying to state they have one accelerometer and they would like to put it into two different signal conditioners. I think the more proper way, that's how I read into the question. So I would use one accelerometer, one signal conditioner, take the output from that conditioner after you have a low impedance, a high voltage, and then split it off to whatever you're doing. If you're going into two different data acquisition systems, two different analyzers, I would take the output of using the proper input-output grounding scheme of one amplifier, one cable, one accelerometer, and taking that output and then doing with it what you need to do for multiple channel purposes.
Great. Again, to our audience, looks like we have one more question. So if anyone else has questions, this would be the time to submit them before we conclude our webinar. So it looks like our final question, at least for now, is except epoxy, is there any isolating glue? I mean, glue sufficiently isolating.
Glue sufficiently isolating. I would say that there's probably a good chance that if you go to a vendor like Master Bond or something like that, they have a number of different options of conductive and non-conductive glue and epoxy that may be available. I think you can, and there's been a technique, and our sales guys have mentioned that a lot of customers have used this over the years, is some non-conductive medium soaked with cyanoacrylate that can get you a bond that's fairly simple to do depending on the temperature and frequency response and all that good stuff. So I think there's a lot of different ways. I think we could explore those for you and maybe get back to you if we have some concern on that, we could probably come up with a couple of different links for you if you'd like.
Great. Looks like a clarification from a previous question. If we have a piezoelectric transducer with the internal circuit isolated and cable shield isolated from case, will an overbraid used to extend the Faraday cage of the vehicle connected to the case and the data acquisition system induce noise from inductive coupling?
No, I think as long as it's just tied back at the signal conditioner, right, the overbraid. So this is like a shielded coax, a double shielded coax, and it would be tied back to the signal conditioner, you're okay.
Great. Well, that looks to be the final question. Tim, did you have anything to add in closing?
I would just like to add for this one question, it seems to be not totally clear what the question is. It would be great if you could present that to us through email and let us, either get on the phone or get with you online to answer these questions in more detail, because I don't think you're clearly getting the exact information that we need to know. Maybe there's something in your specific setup, your testing, your application that really we need to discuss this offline. So that's my preference.
That's a good point.
Yeah. And that takes us to the conclusion of today's presentation. So at this time, I'd like to thank our audience and our facilitators for the presentation today and for your time in attending our webinar. We will be following up with a copy of these slides to you via email. And as part of our closing, we hope that this has been valuable information, and we aim to provide you with more valuable content. In addition to the vast resources on our website, www.endevco.com, you can help guide the next webinar presentation by voting for a future topic that interests you. Thank you, and we hope you will join us next time.